Taking a look at question 25 out of chapter 4, section 2. And this one is requiring us to show that it has exactly 1 0 in the given interval. So let's give myself some room to work over here. And this time the interval that we're given is over the entire set of real numbers here. And really the only way I think we'd be able to go ahead and establish that it has exactly 1 0 is to see if we can establish if this is a strictly increasing or strictly decreasing function. Because if we can do that, then we should be in good shape. And to do that, let's go ahead and take the derivative. So taking the derivative with respect to theta, the derivative of theta is 1. The derivative of sine squared of theta over 3 is going to be plus 2 sine theta over 3 times, using the chain rule, times the derivative of sine now. That's going to be cosine theta over 3. And again, by the chain rule, the derivative of theta over 3, 1/3. The derivative of -8 is 0. So now we're just going to go ahead and do some work to clean this up here. So if I'm going to look at the behavior of this, something that I might want to do to kind of simplify this giant term, what I just boxed here, I can rewrite this using the double angle formula. I'm still going to put the 1/3 out front. And then this is going to be the sine of 2 times theta over 3. So rewriting that one more time, we have this. Now, where does this get us? Now that I have it just as the sine of something, we know that the sine of 2 theta over 3 is always going to be bound between positive and -1. But now that's getting multiplied by 1/3. So if we multiply through by 1/3 here, we're going to have -1/3 less than or equal to 1/3 sine 2 theta over 3 less than or equal to 1/3. Where this is going to be important is if we go back to our derivative here. If we take a look at the extreme cases here, or what we can do is just go ahead and add 1 to each of those pieces there, and we get 2/3 less than or equal to 1 plus 1/3 sine 2 theta over 3 less than or equal to 4/3, and that's telling us that our derivative is greater than 0 everywhere. So this is a strictly increasing function. And at this point, all we have to do is show that we can find some point theta where the original function is less than 0. If we can find some other point on theta where our function is greater than 0, we now establish that there's exactly 1, 0 here. So if I went ahead and picked something like negative 100, that's going to safely have this less than 0. And if I were to go ahead and pick r of 100, that is also going to safely have my original function greater than 0. So we are able to go ahead and establish that there's been a sign change. We have a strictly increasing function, and also our original function is continuous everywhere. And if I wanted to sort of formalize a little bit much to kind of, what I'm using here is I'm using the intermediate value theorem. So if I just go ahead and look at the closed interval, which is contained in all real numbers, we are guaranteed a 0 in there. So this, if I restrict it to this, it allows me to use intermediate value theorem. And I got a strictly increasing function, which says this thing has to run through. Obviously, it's not linear, but it does tell me that somewhere between negative 100 and positive 100 that it must cross. And because it's strictly increasing, it can only cross once.